Okay, I think we can start. Good morning, everyone. Let's so the idea, actually, let me share with you. So we are in day 3. So now we will see the solution of the exercise with the streams, and we will learn how to use the mm, graphical interface of the profiler. We have a break at 10:45, and at 11 we will learn how to use graphs. We'll have lunch at noon. At 1 p.m. We'll have the device management, how to use more than one GPU, and later we will have the time for exercises. We have this exercise, but it's optional. It's in case that you want to practice or what you have learned with the, or in case that you have any questions or you want to discuss anything. Okay, so let's start before it's late. So what I will do is I will share my terminal. Screen. So here what we'll do is we will solve the exercise of yesterday with the streams. So what I will do is I will open the exercise, and the first part, oh, this is like a, yeah, this is an error that I need to fix. So the exercise I will copy in the chat, the link. So I can, yeah, I will copy in the chat also the text. So the text says for vectors x and y, replace the relevant heap memory copy with an asynchronous operation, and using 2 different streams. Make sure that the data has reached the device before the kernel launch. Cool. So here what I need to do is here to define the streams. For instance, at the beginning of the code. Well, this as like a good practice to, yeah, at the beginning of when you start either a function or the main function of C++ code to first start with the definitions, because it will make the code more readable. But yeah, maybe this is like something old school, but yeah, I haven't done this since ages. So the type is a heap stream underscore t. So we will call it a stream underscore x, stream underscore y. What I will do here is to create the streams. Actually, I can create the streams maybe before, because we will see that they will take time to maybe we can create them here. So to create the streams, we will need a heap cert in case that there are any errors. And the function is a heap stream create. Remember that you need to send the the pointer of the stream, because the function will write that variable. And yeah, so this will be a stream underscore x. Don't forget the semicolon. And here I will copy paste and edit because we will use a stream y. Okay, so we have defined a stream, we have created them, and this is also good practice when you allocate memory or create something. Define the when you free memory or when you destroy the stream. Destroying sounds a bit like maybe strong, but well, it's the name of the function. So in release resources, if I write this now, I will not forget. So that's my advice. Again, heap assert. Don't forget the semicolon. And this will be heap stream destroy. And the name of the stream, that will be stream underscore x. Copy paste. Oops, I didn't copy. Yeah. And destroy. Okay. So 3 steps: define the stream, create, and destroy. And now we will use the streams here. This said that don't do that. So actually I can copy and paste here because we will edit. The syntax will be pretty similar. Is a heap malloc. Instead of heap malloc, we will use a heap malloc. Oops. Async, because it's asynchronous. Same, heap malloc async. And the only change is that I need to add a new argument, that this will be the string that we will use for this operation. I use for the name of the streams I use x and y to make it more clear. And also, if you notice in the exercise says make sure that the data has reached the device before the kernel launch. If you notice, this is a oops. Okay, I see that again I made a mistake because the asynchronous yeah, what will be asynchronous is the memory copy, not the malloc. But well, this is fixable. It's a delete, and it's good that we have made a copy of it. Okay, so starting again. Sorry about that. So what is asynchronous is the memory copy. So it's a sync, same as sync, and then here in kind, this will be stream y, stream x. Okay, fix. I see that this is duplicated. Maybe I did that for the copy. And what I need to do is before executing the kernel, I need to make sure that the copies have been done. So I will need to do heap stream synchronize stream x, and then stream y. Cool. So this will be the exercise. Just to recap: definition of the stream, create the stream. They said that use the streams to memory copy, done. Stream synchronize before launching the kernel, stream destruction. Cool. So let's save and compile. Make it works, and let's execute. So this will be batch submit. Yeah, seems that is waiting. More waiting. Okay, seems that is starting, running. I can do watch, but yeah, let's do watch. I think something is wrong with my code, because it's taking a lot of time to run. So let's cancel and see what's going on. Let's just learn P5 16. Or probably okay, I'm confused now. Shouldn't take that long, so that's my. Let's have a quick look at what we have done. So we have defined the streams X and Y, good. If string create, we create the streams, that's good. We do the copies here. Probably still shouldn't be that. We synchronize the streams, we call the kernel, we copy, and we destroy the streams. So this must be okay. Let's compile again just in case. And let's do results. Yes, batch submit. Okay, receive data. Also, my advice: if you use watch, please. This will because the problem with the watch is that every 2 seconds you will do a request to Slurm, and you can this will okay, now it works better, since that was something weird with the because I called malloc twice, so it was something bit wrong with the code. When you use watch, my advice is in case that you want to use it, to use -n60. So every 60 seconds, we'll execute sq -me. If you use a frequency that is smaller, you might get an email from the service desk saying that you are running this quite frequently, and the performance of the login node will not be. Actually, what is affected is the performance of the Slurm. But well, just Control C, and now if we do let's learn. It's generated all of these weird, but yeah, the line that is important for us is this one, that the code seems to work. And if you do ls, you will find that you have a lot of files, and the files that we will need for Perfecto, for the graphical interface, will be this one, results.json. So if you're using a MobaX term, you can copy the file to your laptop using, do you see the, yeah. So for instance, here, results.json, you can say download and choose the folder where the file will be. Cool. So I have now this on my desktop on my laptop. So what I will do is I will open Perfecto. That the URL is this one. Ah, well, it's already there, but well, I will copy it again. So here, let me see if I can share this screen instead. So you will find something like that. Let me see if I can make this bigger. No, fine. Maybe let me check one thing that might work to make this the font bigger. Okay, that works. I just changed the I'm using a different screen where I have like a lesser resolution. Fine. Okay. So here in Perfecto, what I will do is I will maybe there is an option to make this bigger. Macros start times cool height. Well, here you see that you have several options. Open trees file. So here I will open results.json. And you will get something like that. Here what we have is execution threads or streams. And if you make this, this line, I guess that you can see the pointer, the mouse pointer, this hand. This is the timeline. This is a tiny sample. So, but if you have like a bigger sample, like a bigger execution time, you will see more. But if I use this, what is? I think it gives a mistake. Let's open the trees file again. That is an error. I will copy the file again. One moment, since that maybe the copy was not done correct. Probably. I opened the file. I did exercises this morning, and it actually what I will do is I will run it again, just in case. Okay, let's share the window again and see if that fixed the. Yeah, it seems that there is something here with the file, but anyway, I'm executing it again to get the, or no, or maybe something that no, it's, oh sorry, it's working okay. It's the that I need to click here on one of these threads, and in that case, when I press Control and I use the mouse wheel, I can zoom in. So here, if you see, this is the timeline, this line, and you see that the white part is the part that is showing the lower part. So if this is the runtime, and you see that there are a lot of operations of HSA, AMD memory pool allocation, AHSAQ create. So let's say this thread is for the heap runtime. What we are interested here is this second thread that you may notice here that we have a heap string create. Actually, most of the time is taken by the first call, heap string create. Then we call again heap string create, and we do a heap. I can make this bigger. Heap malloc, heap memory copy async. Actually, if we make this bigger, you see that well, this is if you see the time is this is a micro 109 microseconds. I think it's microseconds. The heap memory asynchronous and the second call. And here, what you see is a copy host to device. You see the time that is, and you see that the copy is well done in parallel. You see that it is done by one stream and the other stream. Because this is a toy sample, is not taking that much, but in case that the memory copy, we are copying a lot of data, they will take longer, and making this in parallel will help. After that, we have a heap memory set, but you see that it's only this tiny fraction, the one that, sorry, it's here, yeah. Here you can see the mouse pointer. So this is the tiny fraction in white that we are, this is the zoom in. So if we make this, you see that now we have a heap memory set, heap launch kernel, the memory copy from device to host, and the stream destroy. Also, if we make this, maybe you will find this heap free. So this is the whole execution. You see that this is taking 197 milliseconds, the first call. So you see, I think the execution time total must be maybe less than, I think it's less than a second. So yeah, this is the way. So the way is when we use the rockprof, it will generate a JSON file. You download that JSON file and open it with the Perfecto, and you will see the trace. file. Any questions so far? So, okay, it's 10:30. We can either see the second part of the exercise that is using a heap host malloc, or we can, yeah, maybe we can do that at this kind of. Yeah, let's do that. Okay, so let's share this. Stop sharing. There is a question that, yeah, that's okay. That's a good point that I haven't explained myself. So when I say threads, it's more about I would say more the streams, because the are not the, let's say, the threads that are executed on the GPU, because these threads will be, we are talking about thousands of hundreds of thousands, so this will not be represented here. What we see, the lines that we see are the, let's see, the streams will be the, not every single thread. Cool. So let's open the exercise again, and what the only the change that I need to do is to use pin memory. So that's easy because we don't need to change for X and Y. We have the pointers here that we don't need to modify them. What we need to modify is when we allocate the X and Y, we will need to use heap host malloc. And again, remember to do heap cert heap host malloc, and will be the pointer that this will be h.x. This will be m row multiplied by size of double, and let me check if I have. That's it. Yeah, that's the end of the. And I'll do the same with the x, y, and remember to change that we will use the number of columns rather than. So we do this, and now what we need to do is a heap host free. So here, rather than delete, we will do heap host free, and this will be x yes, that must be let's compile the code. Oh, 2 errors. Something I'm doing wrong. Yeah, that is I miss a bracket. Yeah, because I need to go, yeah, exactly that one and that one. Cool. Now let's execute, batch submit. It's running, finishing, and gone. Control C, and now I check that the result is okay. Yeah, it's the same, it's correct. Actually, a way that I can use is can use cat, and yeah, I get only that line. Cool. So now I get a new file, results.json. So if I want, I can download that file and open it with the Perfecto and see if there is any difference. I don't think that we will have much, but stop sharing here. Share perfect. I will open trace file and we'll see if there are any differences. Well, we see that again, the heap string created, the first call takes, well, I mean, a lot of time. Is we are talking about, well, the first call is 200 milliseconds, the second call is 7 milliseconds. And if we make this bigger, you see here the heap host malloc and heap host malloc, and the heap malloc. And let's make this again the asynchronous copy of it. Actually, for instance, in this one, where it's taking the copy, the actual copy is taking 7 microseconds rather than 1, so 7 times. But yeah, again, we are talking about the microseconds, so this is like I don't know, nothing. But yeah, because this is like a toy example. Okay, so I see that not sure if there are any questions or anything that you would like to discuss. We have the next lesson will be graphs. That I'm not sure if either we can have the. Oh, sorry, I didn't see the. Thank you for the question. Sorry that. So I see there is a question in the chat that is, so we could now run two different kernels using the two different streams. And that will help with the performance in relation to using only the default stream for every kernel. Yes, if there are no dependencies, you can run the two kernels in parallel, and that will improve occupancy, and the runtime will take care of that. So yes, that's that will help. We will see later that also we can use two streams, like one per GPU, so you can submit kernels to both. And with the graphs, we will see that graphs is like a more see another way of using streams. We can create the dependencies between the nodes. So my question now is, do you want to have a quick break now? Do you want me to continue explaining the graphs and have a later a break and then the time for the exercise? What did you want to, or what do you prefer to do? Please feel free to write that in the chat. Okay, so maybe, yeah, let's continue. Actually, let me share with you. Yeah, let's continue. I will move Windows from one side to the other. So today, mainly, I will, so yeah, we can change a little bit. Let me show you this. That is that. So we are in day 3. The lessons are the two lessons that we will is a graph API and the device management. So mainly like today will be like a lot of time for exercises. So please feel free to play with them. But yeah, okay. So what we will see is now this lesson graph API. That actually we can do this lesson and then go for a break. Okay, so let me share this tabs tab, graphs. So we have learned, streams. So we can have several streams that they execute. We can have either memory copies or the kernel execution in parallel. Let's say, concurrently. But the idea of a graph is that, so on the, you see my mouse pointer. On the left-hand side, this will be a stream. So you execute A, later you execute B, later you execute C. So you see that there are like some sort of, say this is the timeline. What you can achieve with a graph, and actually this the runtime will manage to like schedule the task in an efficient way, is to create a graph. Each node will be a task. A task will be memory copy, memory memset, kernel, or a CPU operation as well. And the edges will show the dependencies between the nodes, so between these tasks. The type of graph is a directed acyclic graph. That is normally use the acronym DAG. So yeah, this is the graph. Now we will see how to create a graph with heap that I spoiler is not that I mean not that easy. You will find that we will need to use more than one line of code to define a graph. Okay, so similar to streams, we need to define the graph, create and destroy the graph. Definition here. So to create the graph, we set the variable by reference, and then the flags will be 0, and the heap graph destroy. And with that, we'll free all the component nodes and dependencies. Here, what we will do is we create the graph, and we will configure the graph. And once that the graph is configured, when I say by configuration is to create the nodes, and we will, when we create the nodes, we define dependencies, etc. And we will launch the graph and then destroy the graph. So this will be the, so actually we have the graph, and here we will have the graph execution. That is a different. So we have a instantiate, launch, and destroy. And here, well, the graph execution, that the variable that we have just defined, my graph, and well, this will be null, null, 0. As I said, the graph node types, we have 4. Will be heap memory copy, heap memory set, kernel invocation, or a CPU function call. When we define each node, we will need to define the, if for memory copy, we set the destination and source. For the node, we will need the same. For the kernel invocation, normally we specify the number of blocks, the number of what we have, blocks, threads per block, the function, etc. So we will need to specify that. Okay, let's start with the kernel node. So suppose that we have a kernel with this syntax. That this is the name, we have 2 arguments, and we will use a structure called heap kernel node parameters, and that the structure will contain a pointer to the function, a pointer to the kernel parameters, that this will be a list, and here the number of blocks and the number of threads per block. So the way of defining that is we will need to define a heap kernel node. This will be the type and the variable, and we will initialize this to 0. Here I define the list of arguments that will be A and dx, and these are the variables that are inside this structure. So we use dot to access these variables inside the structure. So the function will be my kernel. I do here a casting of this function. The arguments that I have defined previously for kernel parameters, blocks, the definition of the blocks, and the threads per block in read team and block team. Once that this is defined, I create a node, and I add the the node to the graph with the heap graph add kernel node. So you have the node that we have defined here by reference, the graph that I have already created. I think null is because there is no, let's say, dependencies. That this could be wrong because maybe the DX, there is a memory copy that will be dependent, or and the parameters that I have just defined on top of it. And when I run this, I will get the handle of this kernel node here in this variable. So this is for a kernel node, and well, this is the syntax. Sorry, yeah, I need to define here the dependencies and the number of dependencies. So if there are no dependencies, the third and fourth argument is a null and 0. These two arguments. Okay, so this is for a kernel node. What about a heap memory copy node? So it's similar. Well, I need to define is bit more complicated or more because with graphs you can do let's say a lot of complex operations. So here I have the pointers, source pointer and destination pointer, the position, that this will be the offset in the both source and destination, in case that you have a long array and you want to do a copy of the not copy the whole array, copy a section of it. Heap memory copy kind, that is will be from device to host or host to device, and the dimensions of the what I will copy. You can find further details on the documentation. Let's see if that link works. Yeah. So here is explaining more the extent. Well, let's say that it is not that much, but well, this is what the definition. And well, let's we want to reproduce this on a node graph. So you see that we have a destination. We are copying here from host to device, and we are copying end data or size of table. So the parameters will be these ones. Kind will be heap and then copy host to device. Also for the, yeah, this is a little more, we will need to execute this make a heap position, because we are not having any offset, so we are using 0, 0, 0, the same. And for the pointer, the source and destination, I use this function, make heap each pointer. That you see that the arguments are the pointer, the size, the number of elements, 1. What you can do, they say that for one-dimensional allocation, so you can write a function that will hide all of this complexity, so will make the code more readable. But yeah, this is what they said, that this line, let's say using graphs, is translated to all of this. Well, not this line, part of this line, because now what I need to do is to do heap graph add memory copy node. So this will be the memory node, the graph that I'm using, and here you notice that I put the dependence. This node is dependent of depends on the kernel node. So when you execute when the kernel node finishes the execution, this memory node will execute. Number of dependencies is 1, and what the parameters that we have defined here. Checking this probably is a typo. Is must be M node. Yeah, here I have all of the structures that I'm using, functions. Yeah, this is like the API documentation. When we launch the graph to yeah, so I just seen that there is a question in the chat that if graphs is a feature in CUDA. It is. Actually, let me check CUDA graphs. If I'm using Google, it's the same. And we have actually, let's have a quick look. So we have a kernel, CPU for function call, memory copy, memset, aware. Okay, here we have events, external for conditional node, memory node. So we can have yeah, you see the syntax. You can see that the syntax is pretty similar. So we have learned about a heap graph create, but if we use CUDA, what is the translation? CUDA graph create. Heap graph node, translation, CUDA graph node. See, the parameters are same. I mean, same, yeah. And also the use of the streams. So what we are learning here, we're learning heap, but if you need to use CUDA, it's pretty similar. What it changes is the name of the functions, and but let's see, the concepts are the same. Let's see the graph memory nodes. So you see like here like a more complex structure. Well, this is the code of the. So if we move back to the presentation of this here, we can do before to ensure that the graph is complete, heap string synchronize, and also there is another function that I haven't explained before, that is a heap devices synchronize. So that will synchronize all streams running on the current device. So the exercise that we have now is to translate that. We have a template here. This exercise a digger heap, and we will do we will replace the single kernel launch with execution of a graph. Also, if you want, you can do you can also define the memory nodes. My advice is to go step by step. You can, for instance, first create a node that launch the kernel, and then you can play create the memory nodes and see if yeah, regarding performance-wise, I don't think that we will get like a huge improvement, if any, but this will be the exercise for. Well, you can also. Okay, the advice is yeah, to use a kernel, and when that kernel node finish, you can use a hidden memory copy from device to host. So the graph will have two nodes. Okay, so this will be the exercise. We'll have we break now at. Feel free to have the break or continue with the exercises, and yeah, we will have time for exercises until noon. Now this hour 11, we'll start with a small break, and then we'll be. So this exercise is here. I think we have used it for. Let me check. I think that exercise comes from this one, section 203. Was the first time that we saw this exercise. Yes. But the template will be here, will be in graphs. No, here in the graph launch. So here in this, I will copy that on the chat. I see that there is a question in the chat about the benefit of using the node, using a graph rather than. In theory, I need to be honest. I haven't tried that, and I cannot tell you like let's see a real sample saying that this approach will be better. But using nodes for kernel executions, memory copies, etc. In theory, the performance will be better because the runtime will know how to schedule the different nodes and will play with them in order to get a better performance. But in practice, yeah, not sure if over the lunch break I can find more about your question, and I'll let you know. Okay, so we are close to the lunch break. The plan for the afternoon will be. Well, actually, I'm sharing this, so I can reuse the. So for the afternoon, we can see if you want, we can see the solution of this exercise, and we can explain the device management to how to use more than one GPU. This will be an optional exercise in case that you want to play with the things that we have learned, with the concepts that we have learned so far. So what I will do is at 1 p.m. If you want, I can solve the exercise of a graph. I can explain how to use more than one GPU and explain the exercise, and the rest of the afternoon will be for to play with the exercise. In case that you want to leave early to catch up with some with other projects or other tasks, you will be free to do so. If anyway, I will stay around until 4 p.m. So you will have me to in case that you have any questions or any or if I can clarify any other concepts of the course. So it's a lunch break, and see you at 1 p.m. Have a nice break.